I've now set up the oscilloscope and connected to it a simple dynamic microphone. And if I speak into the microphone, hello, I can see I get a signal. Now what I'm going to do at this point is I'm going to sing a short note, using the word sing in the broadest possible sense of the meaning. And as I'm doing that, I'm going to have to adjust the time base for the horizontal so that I can see a reasonable display. So here we go. Right, now you might have noticed that was a very difficult display to actually see. But what we're going to do now is use a facility of the oscilloscope called taking a single shot. So I can literally take a freeze frame of just one scan across the screen. So let's try that again. Now, I've just taken a snapshot. And you'll notice this is a very, very complex trace. The oscilloscope is trying to work out what the basic frequency is, and it tells me it's about 7.43 kilohertz. That's basically impossible because my voice can't get that high. The oscilloscope's being confused by high frequency components. What I'm interested in is what is the fundamental frequency of that note, because it's actually a mixture of notes, like playing a chord on a piano. It's many notes, many frequencies superimposed. But what we're going to be looking for is what is the fundamental frequency. The lowest frequency has the longest period. And so what we're going to try and measure is the time of the repeat, the longest repeat. And you can see there's a spike there that seems to repeat itself periodically. So that distance, there to there to there, or one of those distances, corresponds to the fundamental frequency. So what we'll need to do now is zoom in on that to have a bit of a closer look. And I'm going to select the cursor again to measure time. So we'll go to select cursors, manual cursor, time measurement. Now I'll select cursor A, and we can adjust the position of cursor A. And what I'll do is I'll put it on one of those big spikes there. Fixate that point. And then let's select cursor B. And I have to gradually move cursor B up until we see where the repeating pattern is. So I think from there to there gives us some idea of what the fundamental frequency was of that note. And we can see there, we can now read off the screen. The important thing, we're not really considered in the absolute values of where cursor A and cursor B are. What we're interested in is what is the time from there to there. That time, 7.20 milliseconds. 7.20 by 10 to the minus 3 of a second. The frequency is the reciprocal of that. And the reciprocal of 7.20 by 10 to the minus 3 is 138.8. 138.8 hertz, about 139 hertz. And that gives us a much better idea of what the fundamental frequency of that particular note was. As you can see, the oscilloscope is very confused. This 7.43 something kilohertz, it is picking off the very high frequency components there and measuring the frequency there. There are other frequencies involved in this note. Let's just have a look at one of the other ones. Let's see, we're on cursor B. Let's just pick where that crosses the axis there. I'll go back to cursor A. And what I'm now trying to do is look at the period of this bit of the signal in here. Actually, I can probably even expand the trace out a little bit. Put cursor A on there. This is the beauty of a digital oscilloscope. You can take your snapshot and alter the time base, expand it out. And there is basically one full cycle of that motion. 1.92 milliseconds 521 hertz. So there was a base frequency there, what was it, 139 hertz, about 140 hertz. And yet there's a component sitting on top of that that is about 520 hertz. And so the human voice, particularly the low notes that we generate as part of speech and singing, are actually quite complex things with many frequencies in them. And one of your tasks today, or when you do the experiment, is to take the microphone and you're going to have to try and sing and hold the lowest possible note that you can, and take a snapshot of the trace and measure the longest repeat period to get an idea of what's the lowest note that your voice can make. And then you can have a go at generating the highest possible frequencies your voice can make. And again, take a snapshot of it with a single trace and make some measurements on it to work out what the period and frequency is of that highest frequency. And we're trying to determine what is the range of frequencies that humans can make.